Okay, I think we can go. Yeah, let's go. Pavel, you know Pavel? You don't know Pavel Dvorak? We worked a lot together in the past.
Okay, so today I will talk about the paper exponential separation between powers of regular and general resolution over parities, which I have with Srikata and Tarhead. I'm not trying to read their surname, maybe so help. Yeah. So it's about generalization of resolutions called linear resolution or ResLin. So who knows what's a resolution proof system?
I've heard about.
You heard about it. Okay, so maybe I will define let's try we had like what's a linear resolution system? It's generalization of resolution, and it's the following. You have some unsatisfiable formula phi, and you want to prove that it's really unsatisfiable in some proof system. So in standard resolution, you resolve just the variables. Here you can resolve like linear forms. So you operate an object which is called linear clause. So what is a linear clause? It's all of linear constraint. So standard clause, it's like x or not y and so on. So you can understand it as so if you have standard clause, let's say x or not y, standard clause, then you can understand it that it's a system x equals 1, y equals 0. So this is somehow easy linear constraint. If this is if you replace it x equals 1 or y equals 0, if you replace it, for example, I don't know, like x plus y, x plus y equals 0, y plus z equals 1, then any assignment of the variables that satisfy at least one of such constraints satisfy this linear clause. So today I will be talking only about linear constraints over F2. So there will be no other field, just F2. So we have this object, and what's in this ResLin system. ResLin system, we have the initial clause are the clauses of the formula phi. So we have the formula phi is let's say CNN, and we have two rules in this system. One is a resolution rule. And if we have two linear clauses in a form some clauses and one particle linear form, let's say L equals 0, and we have the same clause, but the last linear form is L equals 1, and L is some linear function over the variables. From these two, we derive the linear clause C. So this is the same as in the ordinary resolution, where here we resolve only one variable. So this is the
Mhm.
uh, the different, and the other one is a weakening rule. Weakening rule. And
Mhm.
and from some linear clause C1, we derive clause C2 with
more, no, if C1 is true, one of them is true, so C2 would have more disjuncts.
yeah, like any how is it?
So you can do,
Here I'm always confused,
yeah,
but
so you can take C1 to C1 or something else.
yeah. So C2 is C1 or something. So yeah, so this is a system I'll be talking about, and I will talk about like in a dual view of it, which I prefer because I'm not the proof complexist. So we always translate when we read like with the authors any proof complexity result into like
Decision.
decision tags or something like that. So what's our goal here in the system, right? From clauses of phi, we want to derive the empty clause, and this will be by applying these two tools.
Right, so if phi is not satisfiable, you can
Yeah.
show there always exists a deduction, right? Where you start with the clauses of phi and you derive the empty clause,
Yeah.
right? That you could show.
And so what's the dual view on this? So so when we apply this rule, we can somehow organize this rule into a directed acyclic graph, which describe the application of the rule. So we have a directed acyclic graph, which describe the application of the rule. Right, so we have some directed acyclic graph where there is a
Oh, yeah. So somehow the,
so if we have a, let's say if we have this resolution, right, and there is a node with two parents. Each node is labeled by a linear clause. The root is or maybe here there is only one sink, and there is a multiple sources, right? The sink is labeled by the empty clause. The sources are labeled by clauses of phi, right? And in the graph, a node with two parents represents the application of the resolution rule, and the node with one parent represents the weakening rule. Now, if we basically the resolution reputation of the formula phi is somehow bottom-up deck in this picture. If we go top down, we get something we call affine deck. And because if we negate a linear clause, right, then we get a conjunction of linear constraints. And assignment that satisfy conjunction of linear constraints creates an affine space. Right, so if we basically negates all linear clauses which are on the nodes, we get a deck. So resolution is bottom up. Affine deck is top down, right? And I said we negate all the clauses that are labeled on the
On the graph.
on the graph. So what we get now, the things became the root. We have here the whole universe.
Right. Because
So let's say phi has n variables. So the root is labeled. Now each node is labeled by one space. So what does it mean that, let's say, look at the one leaf, or right? So what is the meaning of this affine space? So in the resolution graph, this node was labeled by a clause of phi. So this affine space somehow represents the negation of the clause. So it contains exactly the assignments that falsify the clause. So there exists some clause of the formula phi, right? And for all x in AL holds that
no, it's more than that, right? X
exactly
in AL if and only if C of X is
exactly.
zero.
Yeah, and x. Yeah, it's negation. So x falsify C. This is the right proof complexity. I label symbol. I don't know.
Which is like okay.
No, I don't know. Maybe, but like
Right.
you know what I mean.
So that means that X does not satisfy any of the equations of C.
Yeah.
So that none, meaning it satisfies every negation of the equation of C where you flip 0 to 1.
Yes, exactly. And so what's the dual view on the resolution and weakening rule? So
Because you can't obviously do this on a different field than F2, right? To do this, right? Because if you negate the clause here, you get an affine space, but that's not true if the equation was over F3, right? Because then the negation would say X plus Y is not 0, meaning it's either 1 or 2, but that's not a linear equation anymore, right? But here it turns out we're lucky.
yeah, like there was as we discovered by our reviews, like there is a linear resolution over other fields. We have no idea what it is. So
oh, there's a different rule.
Yeah, like actually, like first mentioning of linear resolution, it was over integers, not over S2.
Oh, I see. Okay.
But that's I cannot tell more about this.
And so resolution works, but I guess the resolution is just you have two contradictory constraints, you can remove them. But if you do the dual,
Yes.
then you have something.
Yeah,
The
exactly.
dual view is not a. Well, it's not nice, it's like.
Maybe, yeah, maybe.
Yeah, exactly, yeah.
Yeah,
But also if you have like inequalities, it was over like R, say, you had inequalities, right? The negations would also be, now then it would be systems of inequalities, maybe some strict, maybe some not. But then it would still be like half spaces or something. So what the set would be like polytopes. Okay, cool.
okay, so now, in this dual view, what's a resolution and weakening rule?
Oh, yeah, what's,
So the resolution rule is basically querying. So you have some node with a affine space A, and you have some linear query L, and you query the input according to this linear query, and here let's say it's A0, which is a restriction of A. A with the inputs that L on this input is 0.
Mhm.
Right, and on the right node we have A1, which is defined analogously when you have one here. So you somehow part this affine space on two subspaces according to this linear constraint L. What's a weakening? You have some affine space A. Here you will have a affine space A prime, such that A is a subspace of A prime.
A prime is smaller.
A prime is a bigger, right? Because
That's
this
like
weakening rule now
that's like forgetting, right?
that's forgetting. You forget some, but
Buried, right? Buried, yeah.
here, right? What's the somehow difficulty of this thing is maybe you arrive to this node right by some queries, but here you don't have to forget these queries. You maybe change the basis and forget something from the new basis, right? Or like let's say.
Wait, but the rule, that's not what the rule said, no? I mean, but the weakening rule, in the weakening rule, it's like you took C1.
Maybe it's not it should be semantically implied, like that's maybe it's not written here, but what can happen, right? Let's say we go here, we have that x plus y equals 0. We've got here that y plus z equals 1, right? So affine space is a space that of assignment that satisfies these two. And here the A prime can be, for example, x plus z equals 1. That's
I see. So there's something else in the weakening rule that would say like D is implied by the other?
Yeah, like
So it's
that is a proof complexity, like the notion I don't like, but that somehow C2 is semantically implied C1.
Oh.
I'm always confused what does it mean, but it means this.
Okay.
Right, so we have this affine there, right? And so which behaves like this. And what's this property? It computes something we call let's say search pi. And the goal is somehow we have an input assignment of variables, And the goal is to find a clause of phi that is falsified by this input.
Okay,
Phi is
can I recap for my sanity? So, primal view or proof complexity view, you have a CNF phi. What is that? That's a collection of clauses.
yes.
Each clause is a disjunction of linear equations.
This CNF
Is
is
a
a
conjunction
of
of disjunctions of linear equations.
like usually we say that these clauses are the ordinary clauses as we know it,
Right,
but maybe
right.
for like this system is more powerful than standard resolution. Somewhere in the middle is somehow useful to use this linear constraints.
Oh, I see. So you're saying that
See, and this phi is standard.
I see. So you're saying that typically when people in proof complexity look at what can be proven, they start with the standard CNF,
Yeah.
right? But somewhere in the middle,
And
somewhere in the middle, you might have added, how can you add it? It's only the weakening, no, that allows you to add stuff,
yeah.
right? I mean, because if you start with clauses that don't have linear, it's just x equals xi equals,
Yeah.
and you just do resolution, you're also never going to get something which doesn't have linear, which has, right? So the only way to introduce a linear constraint is by the weakening.
Yeah, and then you can work with the linear
Right.
clauses. And it's proved that linear resolution is more powerful than standard.
I see. So you can.
Sometimes it makes sense to actually to introduce this.
I see. I see. So even starting with a normal CNF, there are certain CNFs that can be proven using these linear resolution that cannot be proven using normal resolution.
Yeah. For example, in the linear resolution, you can simulate something like a binary search that you cannot do in something like, I think that I'm on a very thin ice on these claims, but like
Okay.
there are formulas that are hard for standard resolution, but easy for present.
Okay. Normal form.
Yeah.
Okay. So that's the primal view. You start with the CNF, which is unsatisfiable, and you want to prove that it's unsatisfiable. And to do this, you can use these two rules, right? Alternatively, you can think of, instead of trying to prove that the CNF is unsatisfiable, you can think of the following problem, which is a search problem, right? I give you some assignment. Let's assume that phi is unsatisfiable. I give you some assignment. Because phi is unsatisfiable, there has to be a clause that this assignment doesn't satisfy. Then I have to find such a clause. And this is a search problem, right? And now, okay. And for this search problem, the computational model that I'm going to look at is these linear DAGs, affine DAGs, right? And now the claim is that there's a perfect correspondence, meaning, and in these linear DAGs, I can do these two operations. I can either query a linear function, that's one operation, and then it splits, or I can forget some linear constraint. So meaning I go into a subspace which contains the subspace I'm in, right? So these are the two operations I can do in an affine DAG. And now the claim is that there's a perfect correspondence between ResLin proofs and affine DAGs for this problem, right? ResLin refutations of phi correspond in a one-to-one way to affine DAGs for search phi.
Yeah.
Okay, got it. We understood. I think.
Okay, so in the rest of the talk, I will talk about this because it's for me like more instructive. Yeah. So far, like there is no lower bound against affine DAG.
Wow, none. Like you want an exponent or something, right?
Yeah. Like
Super-polynomial.
yeah. So there are some restriction of it. So as you see, there is this regular thing, so which will there is a
so there's no lower bound for affine DAG, but there's a lower bound for regular.
Yeah. So what does it mean? So in standard resolution, there is a subsystem called regular resolution, And in this deck view, if you look, so what's a regular in a let's say cube deck. So if the object here are not affine space but cube, then this is exactly object which corresponds to standard resolution. Because in standard resolution, we resolve only variables, so there is no linear query. So the affine spaces becomes cubes, but
becomes Boolean subcubes.
yeah. So if you look on any path in this deck, then any variable on this path is queried at most once. So if this holds, then this cube deck is regular. Right? So this object is something between cube deck and decision tree, because for decision tree it holds, right? But you can have a directed acyclic graph and somehow the queries are made in this. So it's some intermediate somehow.
And now it's going to be that along any path, it's linear independent.
Yeah, it would be nice, but we don't know about. We need even a stronger restriction.
Oh.
So now we call it a bottom regular.
This is still a normal deck, normal cube.
No, bottom regular for like bottom regular affine deck. Now back to affine deck. So this thing was defined by Gryazov, Pudlak, and Telepanfar 2 years ago. And so what is this bottom regular? Take a node in affine deck. Let's say take node U. Look on this node in all paths.
Look at the subtree.
Subgraph. It doesn't have to be tree, but basically, and take all queries. All queries made in this graph. Not only on one path, but and make a linear span of it. So make space of all queries in this tree, and we call it this space post U.
So the space of all, you mean the span of all the queries under U?
Under U, yes. And
okay, yeah, that makes sense.
right.
So that's a link. That's Nathan. That's not a Nathan. That's.
So if there is if we make like L1 query L1 here and L2 here, right? But L1 plus L2 is in this space, even though L1 plus L2 was never asked in this.
I see. So it's the span of all the queries, meaning I see. So I actually care about the coefficients that appear in these linear equations, and I think of them as vectors, and I just take the span of all these vectors.
Yeah.
That's subspace. And that's a subspace, yes.
And so the affine deck is a cube regular. If
no, bottom regular.
The bottom regular. If for any edge VU, so there is a vertex V, there is an edge into vertex U, right? We make, let's say, this query is a LV, is the query we make in V. And let's say V is a query vertex, right? So for
LV
each edge where V is a query vertex,
LV is not in post U.
exactly, LV is not in post V. So this we call the
No.
no. So this we call the bottom regular. If we have a regular cube deck, it's a bottom, actually a bottom regular. Because somehow,
You think they're the same definition?
yeah, it's because somehow, like if we have cube deck, then everything is written in one basis and and so actually, like why this is like you have this bottom right, you can define the similar way pre-V that are all paths that goes to V, right? We call top regular something that like the LV is not in pre-V, and then again it holds for so top regular is that LV is not in pre-V.
No, LU or LV, LV.
Yeah, like because like LV is in post V, right? By definition. So here is defined according to edges. LV is not in like does not have to be in pre. And then there is a well, something that's stronger level.
Which is both.
It's
not.
is that post V
There are
unit intersection 3D
zero.
is like contained on the zero way. So it's enough. So funny thing, like in this paper they actually define only top regular and strongly regular, and they prove a lower bound for function for strongly irregular thing. We actually don't know was like if top regular is more strong than strongly regular, and there is a it's not known how this the relation of this. So GPT defined top regular and strongly regular. Then there was but for function. So GPT proved lower bound for function for strongly regular. And there was Efremenko, Garlík, Itsykson last year. This is a stock paper, and they prove lower bound for bottom regular for search problem. They prove that binary pigeonhole principle does not have like a sub-exponential bottom regular finder. And it's funny in both two papers, like GPT called top regular and AGI called bottom regular. And we somehow stem on this paper. They prove the lower bound, and we prove that there is another formula which is hard for bottom regular, but easy for standard resolution. Even for ordinary resolution with no regularity restriction. So that's the result I will present.
Okay. I see. So you're going to give us a formula, and for this formula, you can prove a lower bound on bottom regular resolution. Nonetheless, it's actually easy for usual ResLin.
Yeah, even for ordinary
Oh,
resolution.
even for ordinary resolution. Oh, I see. Oh, okay.
Okay, so is the model and the problem clear?
But the Garlík, you proved another lower bound, or you proved what?
Like they gave a formula that is hard for the bottom regular, but it's quite hard formula and it's probably also hard for ordinary resolution. So this formula does not prove the separation of two models, only that there is a hard formula for one model. So we completely cannot say that like we generalize the result because our lower bound is a little bit weaker because like they prove that size of bottom regular, a finite for that formula is I think 2 to n to 1/3, and our lower bound is 2 to n to 1/14, something like that. So we have a weaker, some instance a weaker lower bound, but their formula is much harder. So probably also hard for the structure.
Mhm.
Okay,
So give me just a second. So what's the relationship between resolution DAGs, normal DAGs, and branching programs?
Yeah, the thing is like the standard branching program.
What's the forgetting that has to be structured?
Yeah, like because like
In the standard
like
branching
in
program,
standard branching program you cannot
you can merge anything. In the standard branching
you
program,
can merge
merge
anything.
Whereas in I see. Whereas in a query DAG,
Like,
you merge.
somehow the inputs that are like that you will get into one node does not have to be like a fine space. It can be like quite long.
Understood. Yeah.
Like the thing is in our paper and also because of this Efremenko paper and Pudlak paper, like we work with more with a fine deck, but call it a branching program corresponding to prove that there's a little bit mess in these three papers with the names, but also because of we are new to proof complexity, so but let's call it the deck in this lecture and
But it's a very strong, I'm guessing it's a very strong constraint, right? When you say that, like the
Yeah.
set of strings that correspond to this place somehow has to have this structure, you're like a branching program just doesn't care about this at all.
yeah.
That's interesting. Okay, got it.
Okay, so what's
Yeah, all right.
what's our hard formula? So it's a list of formula that was used for separation of ordinary resolution and regular resolution.
Mhm.
So, or maybe so it's a list of obfuscated stone formula. I will define formally. So this stone formula and the obfuscation was used already by Aleknovich, Johansson, Pitasin, Urquhart in 2002. For, as I said, for separation of regular and ordinary resolution. Interesting thing, they gave several formulas. One was somehow the stone formula. Another was that when they use the obfuscation, I will define it. Somehow we need both of these techniques in one formula for us. I think it's not needed, but somehow we cannot. We have proof only when we use both these techniques together in one formula. We didn't have much time before like the line of CCC that we can somehow simplify the formula. So what is it? So the stone formula, you can somehow define it for arbitrary directed acyclic graph with our degree 2, but we use a pyramid graph. So we have a pyramid graph with a layer. So how this look like? So there is one rule. And so on. So in each layer there is one more vertex, and they are connected in this way. So we have n layers and say capital M vertices, which is roughly n squared. And on each vertex, we put a stone. So we put the stones on the vertices. Each stone has a color, red or blue. And the formula said that on the root there has to be blue stone. On the sinks there have to be red stones. And
If there's a blue stone, one of the children has to be blue, something like that.
yeah. If you are blue, then so if you are blue, then somehow
That doesn't.
this configuration is forbidden, right? So the formula describe this. So this is stone formula. I will talk what's the obfuscation, but this is clear that this formula is unsatisfiable. Right? So let's look at it more formally. So what's the variables of this formula? So we have
XV for each node V or something?
we have PVJ, which is 1 if stone J is on vertex V. Right, this is the stone assignment.
Oh,
Then we have a color, which is 1 if stone J is red.
oh, so it's not just some variables for each node saying whether
No,
it's red or.
No, the thing is, there is this stone thing. That,
So
this
you
is
have
the one technique that like that we have variable for the color and then the assigning the stones. So this is one technique used by these people to prove the separation.
So this is some kind of pigeonhole thing, because you have to distribute the stones through the vertices. And on top of this, the coloring has to be somehow.
So
Yeah, and then the last variables are somehow the DL, which are auxiliary variables, because for lifting, we need only constant size clauses. Otherwise, like the lifting would blow up the formula into exponential sense.
Okay.
So these are the used variables. It's some index. You will see.
These are the variables, and your clauses encode the blue. What is that?
Yeah, I will talk about the clauses as well. So, what are the clauses? One thing, you will see from the clauses, but like there should be at least one stone at each vertex. But that's the only condition. We can assign one stone to many vertices. We can assign many stones to one vertex. That's the only stone. There is at least one stone in each vertex.
Okay.
So one thing is all stones on the root are blue. So these are, so let's say root, the name of the root is R. So PRJ imply not RJ. And this clause we have for all stones J.
All stones J that are assigned to the roots are blue.
Yes. So similar ESJ implies RJ. It says all stones or things are red. So we have this for all J and all things. Right. So this is the same. Then we have this for the big clause. No, sorry. It's the other way around, right? Yeah. So this says each vertex has at least one stone. And we chose this big clause because these has a size capital N. The number of stones we use is also capital N. And vertices and N. So we don't actually use this, but we chop it with these z variables that we have the equivalent set of clauses. So we have a PV1 or Z or not ZV1, ZV2 or VV2 or
Is this the obfuscation?
no, this is I'm not there yet. I'm just so this is just the last one.
You make any CNF into a 3CNF.
Yeah, it's a standard thing that's
V1 and V2 in the second.
yes. So this is just chopping up the large clause to the small one. So this, right, so this is the. Now, the obfuscation will be used for the induction clauses. So now, how to encode this thing. So, we said induction clause. So we have it for V is a node with two children, so non-single node. IJK are three three stones, and we have that. So we have V and two kids of V, U, and W. So we have if we put a stone I on the vertex U, which is red, and if we put stone J on W, which is red, and if we put a stone K on V,
It must be red.
then it implies that. Okay, and now the obfuscation. So we want to obfuscate this clauses. So for this, so let's say this is a set of variables V. We have some obfuscation mapping. Map along. Oh, this is and so raw, which is mapping from triple of stones to the set of variables. Now we obfuscate this clauses. So instead of taking IJK call, we take IJK or raw IJK and IJK or not raw IJK. I'm not. We need some property. I will about raw. I will talk about it later. But so this is the thing we call obfuscation.
So this row, oh, sorry.
Like
Oh,
IJK are some triple of stones, right? Raw is raw of IJK is some variable.
but the same set of variables from the same set of
Yeah,
variables as before.
we have this variable.
And you take all of them, not just only the assignments, colors, or auxiliary ones. Could be anything.
Yeah. Like the thing is, right? Why this was technique, right? To make the formula hard for a regular resolution, right? Like you can resolve these two easier, right? And get the original problem. The thing is, when you resolve it, you cannot resolve it anymore, and you maybe need to ask it again later. So
I see.
so that's why if you pick raw like
At random?
yeah, it's a random random function has the property you need for this. Then okay, so this is the formula which we call so this is a formula which we call a formula of pyramid on n-level pyramid graph obfuscated by right? So this is a hard formula for a regular resolution because already without obfuscation it's proved that it's hard. But we need to say that it's hard for quantum regular ResLin, so we use lifting. So we use lift by inner product gadget. So we have inner product. Where B is a logarithm. And we lift this formula by inner product gadget. So maybe how this lifting works for formulas, right? So this formula is set of clauses. So let's take some clause C, right? And actually, by lifting, we change the C into a set of clauses. And when we take these sets of clauses for any C of the original formula, we have now the clauses of the lift formula. And how we create this? So somehow,
for each old variable, you have a new set of pairs of variables.
Yeah. So if we have a variable in C, then each of these clauses, right? For each variable, we have B new variables. So we have some Y1. Right? So and we created this clauses in a way that this clause C has exactly one falsifying assignment. So alpha is a defalsifying assignment of C. Right, that they take C as a clause. This is a assignment of the variables of C.
Oh, because if you have a clause, yes, there's only one set of
Right.
falsifying assignment.
And now we create a
Yes. I see. And now the inner product must be equal to this satisfying assignment. This falsifying.
Then if any we create these clauses in a way that any falsifying assignment beta then for this holds that if we apply inner product on beta, we get like blockwise, right? Because we have a block of B variables for each variable here.
So I think I understand.
Like the semantic of this.
So you replace C with, for every pair X, Y, that if you apply the inner product, you get alpha.
So you constructed these set of clauses in a way which describe that the image of beta differs from alpha in at most one way. That's somehow what the semantic of like I can write it formally, but
well, no, I'd like to understand actually what's the.
So you can also think of it as, so you have this clause C, and now you want to write the clause as C composed with inner product. Now you can think of C composed with inner product as a Boolean function.
Yes.
Which takes in B times width of C variables.
Yeah.
Your output 0, 1 if the clause is satisfied, 0 if the clause is not satisfied.
Right.
Now every Boolean function can be written as a scalar.
Oh.
And you just have to do that,
That is CN. Is it
so you can
a clause is a node of variables?
The clause is also a function.
you can say you make a conjunction
So you
of
negate.
any preimage of alpha. Right, let's try.
No, so is what, so you take a clause, it's a disjunction, you negate it. So any clause is a negation of of an and. It's a negation of an and.
Clause is the
Right. So now you replace this and, is that it, with the inner product?
Let's say so you have this
Right.
falsifying assignment alpha.
Right.
Of C. This
And
is
a clause-
assignment only of the
Right, and a clause is exactly, the variables are not equal to alpha. Right? It's not, the variables are equal to alpha. Right?
Yes.
And then you can also write not the inner product of the alpha of the
Yeah,
first two
so-
guys is alpha one, the inner product of the second two guys is alpha two, right? And now you have just a big CNF, and I will negate this, and you get the set of clause.
Yeah, like you can take a like conjunction of
Yes.
all preimages of alpha. Right? And your disjunction says
You're not
y
equal
is
to- yeah.
is not beta.
Exactly, yes.
So your disjunction is a y is not equal to beta. This is a
Wow.
these are the clauses of this.
Right, where y is actually,
Y is
oh, I see, yeah,
the block, the variables, the delimited variables, the blocks.
Right. Yes, that's exactly what.
So
what it is.
one important obvious thing like which is used later, observation, if there is x in C, then here in these new clauses all variables corresponding to x are present. That's something some technical observation that we will need.
If x is in C,
Right?
if x satisfies the clause,
No, x is a variable of C.
oh, if x is a variable of C, yes.
Right? Then the corresponding, like we introduced a block of variables for x,
Uh-huh.
right? And in all clauses that we create for C, right, contains all the variables, right? Here, right?
Right.
You
No,
will-
yeah.
If we will get there, like I will repeat it like an hour or two, something like that.
But this is also why you need inner product and not indexing. Because
No, that's like you can always write it in this way, dependent on the function. It's
you write it.
right. Maybe you can sometimes you can simplify, but you can, the inner product because we use a seven.
It's good because it's small, right? So this will blow up by, like 2 to the
Yeah,
power.
we use Yeah. Like we need a logarithmic size only in one place. That we use some heavy machinery of. If you recall this paper of Arkadiev et al. With simulation from like a low discrepancy function. It's like a heavy machinery for communication listing. We use it only for parity decision tree listing. So therefore we need this logarithmic size. That's the place we think can be simplified. But, okay, so this is the hard thing. So somehow few words why this formula is easy for standard resolution. Like the main work is about the lower bound. Why it provides the separation. So just like the standard resolution, right, can follow the blue path here, right, in the graph, and find find a contradiction. Because because
So you
we have
query,
only constant. The important thing is that actually
so you just query all the stones and their association with the root until you find the blue stone. Oh, they all have to be blue, doesn't matter. So until you find a stone that is associated with the root.
Yeah.
You got it.
Then forget the rest.
Then forget the rest, right? To make it small, right?
Yeah, actually you can make it that you remember only like constant width of this.
I guess.
Yeah, you just like query these things and either you find a contradiction or you find a stone which is on the vertex.
Yes.
Right, and you find the stones which are here.
Yeah.
And either there is a contradiction or there is another blue stone. And then you continue.
And then you forget what you've seen before, just remember
Right.
that stone and continue that.
And the important thing is that you can do it in constant width.
The guide itself is constant width.
The width of that is so we have cube deck, right? This is standard resolution. So you in each node,
Right.
you remember only constant number of variables.
Yeah, but does this translate to the guide also having some kind of constant width?
No, it's it's not a graph like a function, like a graph property, but that the cubes on the decks are small. The constant width is important because we have logarithmic size gadget, and then we can somehow simulate this proof in polynomial size of the deck. If the width would be bigger, then we would have like super-polynomial.
So I'm just trying to recall the connection to size from this. So, okay.
Because you have to query so take a proof that is not constant width, right? I think you have to query all the inner product.
I'm just asking in the original. So how do I bound the size? Of the proof. So we want to eventually bound the size of it, right? Not the.
Yeah, but if you have constant width, right, then you have a polynomial size because like each.
Well, you only need to remember where you are in the tree, okay? And that's the tree is a polynomial size, polynomial.
This tree.
Yeah, this tree.
Okay. Yeah, the proof tree would be bigger.
Well, what does the proof tree? So any node in the proof tree has to remember where you currently are in this tree, and the assignment, the stone that you currently have in your hands, and the stone that you're looking at.
So you're saying that you're counting the number of nodes just by saying the memories.
Yeah, and also like if you have constant width proof, right? Let's say W, then the size of the proof is at most N2W, right? Okay, so that's the upper bound. So I'm on the second page of my notes, and there are like now another 6 or 8 pages of notes about the lower bound. So if you want to answer or have a break, then let me know. Okay, so maybe I will.
And that's the point, right? If the width of that proof was not constant,
Yeah, actually,
Because
first
we-
we come on the
right?
like
you need
with other we try to use other formula of this, like where the obfuscation was used, but there was like large with proof of that, or we cannot prove. Maybe it's proven that this formula doesn't have constant weight, so we cannot use the delta weight.
I see. And the point is that you need to query every variable in the inner products, right?
Yeah,
And you need to remember the output of the outcome of every variable, and that's like n outcomes per original variable for a total of n to the width.
I believe.
Okay. Huh. Wait, but are you going to prove a broad lifting theorem for why communication complexity? Because communication complexity is a tree, it's not a dash.
Yeah, because somehow we use the part of the lower bound is a lower bound against 3. So we show that now we derive in a way that we need to prove average case lower bound for decision 3 against decision 3 for search of the stone form, not lifted. But then we need to lift this lower bound to parity decision 3, and for these things we need some simulation theorem, randomized simulation theorem.
Oh,
And we don't have it for like we have for communication, which implies this simulation for parity decision 3, but we don't have like maybe either proof just for parity decision 3.
okay. So the reduction is if you have a regular parity.
It's not so easy. Like, there is a few pages how to get to the lower, how to use why we need lower bound for this decision.
Sure, but I wanna have an overview, right? So you start by maybe can you just give us the steps?
Yeah. So I tried to like get the final argument, and then we will see what steps are needed. So that's right here and then in the bottom. So now we have a find like a P for search of a stone formula on n layers pyramid graph obfuscated by some row and linked with this network line. Right, and what we want to show. Let me. So then size of P, the number of nodes in this bed is at least 2 to omega n to 1/3 over N. So this this n is a number of is not a number of variables, right? It's a number of layers. So this pyramid graph has n squared nodes, and we have n to 4 variables, because we have a variable for per stone and node in the pyramid graph. So, right, this becomes to like n to 1
Number of variables.
right? So. Okay, so this is the main theorem of our paper, and
And
so-
you prove that if it's regular or top regular is enough.
bottom regular, yeah. So if P is a bottom regular and so let's have the root of the P, and let's have some input, sometimes B, where M M is the size of the variables of the unlifted column, right? So this is the assignment for, and we know, let's take an assignment beta and follow this assignment in the deck from the root for T steps, and denote this node by P beta P. That we take some input and follow the path of this input from the root to some node in distance T. Right? And now the thing is that if T is sufficiently small, then we arrive into a large codimension affine space. And this is the idea of Efremenko et al. That they also somehow say this, that if they make a T step, then so roof step. So we prove that we give some hard distribution. That if beta is sampled by this hard distribution mu prime, then codimension, meaning a number of constraints which define the affine space, right? So we look on the affine space which is in this node. So AP beta T. Is at least T with probability 3/5, and this we said this T to be C times n to 1/3. C is some small constant. So we prove that if we set T to this, then means that this is large affine space. Why this So first, why it is implied at the lower bound? How this mu prime looks like. So mu prime consists of basically two steps. Mu prime. So first step is simple alpha according to some hard distribution for the unlifted formula. So mu is a distribution over V, which are the original variables. Then when we have alpha, then we sample a random pre-image of alpha uniformly. Right? So what this so this probability is we sum over all vertices of P of this affine deck such that codimension of AV is at least T, right? And this vertex we have a probability over mu prime that this vertex P beta T is V. Right? This is just and now it's because like the property of the inner product, but not only inner product, but it's something strengthening of stiffling. You are aware of it, right? Of the stiffling, we will use it. If you have like inner product or majority or indexing also, it holds that it's somehow it's a if you have any string and pre-image of that string is by inner product or other, it's somehow pseudo-random against affine space. Like no affine space somehow cannot contain many pre-image of inner product of one string. So because of this, right? Let's take a affine space of codimension T and sample a random string. Then this string is in the affine space with probability 2 to minus. Right? Because this is one thing when we have new things over Efremenko et al. Because their distribution was uniform, and they use this. But because we have, for example, we cannot use a uniform distribution because of this chopping of long variables. So actually, uniform distribution for this problem is easy. So because it needs a little bit of thinking, but right. So, but we realize that because of this lifting, we can have arbitrary distribution here, and when we then it's simply uniform pre-image of hard sample, then it still fools the affine spaces. So we know.
So let me now try to understand what you just said. So you're saying that if I start at the root and I sample an input according to this distribution, with high probability, I'm going to end up in a node whose associated affine space has large codimension.
Yes.
Okay. Now, any such subspace of large codimension, and now what's the point? Cannot include a lot of pre-images or
Yeah, because like,
cannot include a lot of pre-images
what's the
of this.
property of inner product and other gadgets? But let's talk about inner product. Is that
Wait, let me try and finish. Let me just take it for now. We'll see why that's true, but let me just take it as now. So now we're saying that if you have this affine space, it has large codimension, hence it cannot include a lot of the pre-images of all these inner products, right? So now let's assume that it must hold that.
yeah? Let's finish this calculation.
However, like 3/5 of all these pre-images must be in such affine
Yeah,
subspace.
so though you need a lot of them.
You need a lot of them. That's the point. And now, so you're even saying, you're even proving something stronger. You're even proving that if P is bottom regular, then just within the first distance n to the 1/3 of the root, there have to be a lot of nodes already.
Yeah, and basically like this idea like occurs in many like proofs against the regular system. For example, this proof is that basically it's against lower bound against a regular thing. They prove that in the first T steps, whatever T is, the proof has to be 3. The same thing as I talk about the proof of Pudlak et al. Against stronger regular, they prove it as well. The first part of the proof has to be 3. There cannot be not forgetting, no forgetting. So this this somehow is a similar.
In some sense, like you don't know which clause is eventually going to be satisfied, so you can't forget it's out.
Yeah. This basically the idea of this proof is that in this moment you still can like change the clause which will be falsified at the end. So
it's like, it's something like, if you forget, now you use the regular, no, it's like if you forget one variable alone, right? That might, you still don't know if this might be the exact variable where the violation happens. So if you forget it, you won't be able to query it again, right?
It's exactly the idea here. Now, like we are in the affine spaces, so but there is some dimensionality argument which says that if your dimension is something, then that thing will happen.
I see.
Right.
Okay, so
here
property of the inner product, yes.
the property of inner product is that if we have any alpha and we have a uniform random preimage alpha, and we have
the probability
any affine space of codimension T, then the probability that B is in A
it's like 2 to the minus T or something.
is like, yeah, there is some log n loss. It's 2 to minus omega T over log n. When this log n is because we have a log n size gadget. So for so basically this loss is the gadget size loss. Right. So here this probability is bounded that like beta is in AB, right? And Beta is in AV,
Yeah.
right? And each this probability we know it's small, right? And this sum is over the nodes of a large codimension AV,
Yes.
right?
And,
So
and alphas. And alphas.
so it's at most S, where S is the size of the
Number
of
of
the
no,
of the
of
of the affine deck,
Yes.
and this is a 2 to minus T log n,
Hmm.
right? So we know that
Hmm.
this is at least 3/5, so this has to be large. So the main thing is like how to prove this. Yeah, so we have a middle step which says that the probability, if we like sample alpha according to some distribution, and beta is a random uniformly random privilege of alpha, then this affine space is called alpha poolable, which I will talk more about it, but it's a so this alpha poolability in a short way is that as we say this affine space still don't know which clause will be falsified. So okay. So now to define the alpha poolability, we need some linear algebra because so can we continue with some questions?
So every node that has
I didn't define what's what it is. That will take me some time. But I'm saying that there is some notion which we can prove that like a lot of nodes satisfy this notion, and it implies the large codimension of that affine space. There is some like intermediate notion. But okay, so all right. I don't know if, for example, if you want to have a break, then maybe this time is maybe the good time. I don't know. It's up to you. Like
I don't know. What do you say, guys? You want a break now? You take a break.
It depends on how much longer if the next session is very long, I would want to delay the break. If it's not too long.
let me check. There is a yeah, it's like 2 pages of my notes, but of the linear algebra and how it goes with different.
Okay. What is that? That's not all, right? So we break right now?
I mean, I'm breaking.
Huh?
I'm kind of breaking now.
Okay.
Let's do it.
So now I we need to define some linear algebra notion and how is it related with stifled gadget. Stifled gadget was introduced by Arkayev, Suhel, and others in their simulation of PDTs. So let's say we have a gadget G, and we say it's stifled. Give the following out. So for any index B and any bit A, there exists some assignment of the remaining variables. So some delta, which is an assignment of all the variables of the gadget except the each one. There exists such that for any gamma 0, 1 holds that if you set the variables according to delta, so I will try to here you have B variables. You have I index here. You put delta, which is the assignment of other things than the ith bit. You put gamma on the ith bit, then this is always A, no matter how you set gamma. So it's a little bit technical, but adversary index of the somehow variable he can sign later, and result what he wanted at the end. And we know that there is always some assignment of the rest of the variables, that no matter how he set the last variable at the end, the result of the gadget will be the same. So how is it good for like affine spaces? So suppose you have such nice set of constraints. So this is let's have a matrix M in echelon form, right? And A is a affine space of the solution of the system. So I don't know whether as this that like affine space is a set of solution of the system and defined by the matrix M and some vector vectors.
Mx equals C.
Yes, Mx equals C. And so this matrix. So now we are in the lifted world. So like the lifted variables are grouped into blocks, right? So columns of this matrix corresponds to the variables, and they are split into B is size of the gadget, right? And now suppose we have such nice so this affine space is a subspace of M times B. And suppose we have such nice matrix. It is in echelon form, and each pivot is in a different block. So echelon form means you have an identity matrix at the beginning and then something else, right? And then, let's say we have then let's say here in these blocks we have something else. We have a pivot here and then something else. Right, so and so we say the matrix M is safe if each pivot is in different block. Then is also if the gadget G is fitful, then any string has a preimage in this affine space. So then when M is safe in this manner, then we say that
Every alpha has
every alpha there exists beta in preimage of alpha that beta is in and why is it so, right? So how you can generate or get element in the affine space. So the variables where are the pivots are dependent variables. The others are free. It means you can pick any value of the free variables, and this set of constraints uniquely determine the set of dependent variables such that the final string is in the affine space, right? Because each pivot is in different block, then let's look at this block, right? Let's say we have this pivot, right? And we have this alpha. So we want that like this block maps to alpha 1, let's say it's 0. So we want that this block is mapped to 0 by our gadget. We know the position of the pivot. It's only one pivot in that block. So the rest of the variables in that block are free. We can set it anyway. And anyhow, so we set it by this assignment delta. We know the position of the pivot, and we know what the final string should be mapped to. So we set this, right? And in this way, we set all blocks. Even if when there is no pivot in the block, then we set it by just arbitrary preimage of that. But if there is a pivot, right? So we put so this is let's see, the pivot is at the position I. We put this assignment delta and the rest. The constraint said if we should set like this is a variable on the ith position in the block to 0 and 1 to satisfy the constraint, right? But by the property of delta, we know that no matter how we set this I variable, it's always mapped to 0 or 1. All right. So if we have this nice property of the matrix, then all strings has the prime. The thing is, this of course is not true for any effort. So now, so now let's talk about like the space of constraints and how like it turns out what's true for like in simulation theorem that if we fix several blocks, if the codimension of A is small, then we can fix small number of blocks such that this property holds for the rest of the blocks. And it's this is the thing that we had, but we cannot use it, and Efremenko et al. Show the same thing. So what is it? So let's have U, a subspace of this, and understand U as a space of constraints. So rows of this matrix M. Like all I'm saying is not dependent on the vector of the right side. It's all about the matrices. So we understand U as a set of constraints, and we say this U is a spread if any set of k linearly independent vectors in U touches at least k blocks. The vector touch the block if there is at least one either at that block. Right, so let's say you have this vector, so this vector touches these two blocks. If there is only 0 in that block, so when the set of vectors touch a block if at least one of them. Right, so if we have, for example, another. Right, so these two vectors touch this, and this. Right. So now, what's the nice thing is that if U is spread.
K spread or something?
No, it's for any k.
Oh, I see. Okay, got it. Okay.
Or like
Oh, okay.
of course, like k is at most and like yeah.
Then it should be
N times b, but
I see.
it's a spread, and the dimension of U is at most m. Then U has safe dimension, safe basis. And so there's a nice combinatorial proof. If you look at this, it's basically whole condition. If
It's whole theorem.
Hall's theorem, right?
I see.
So the proof of this is basically Gaussian elimination with Hall's theorem.
Oh,
So it's nice, nice proof.
yeah.
Okay, so somehow abstraction to have a safe basis means that there is set of vectors that are somehow concentrated, like lot of vectors that you have at most, there is some k plus vectors that touches at least at most k blocks, right? And so we say definition. So let's have a set of blocks.
And it's an if and only if, no?
This thing?
Yeah.
Probably yes, but we need this it's like if U has a safe basis, It should be right because, yeah, because,
K linearly independent vectors, you need at least K elements from the bases.
yeah,
Oh, but,
The-
yeah, and they can't cancel on the pivots.
yes, yes.
Right.
They can, so, yeah, that's,
They cannot cancel on the pivots.
the other way is, someone.
Yeah.
So, we say the set of blocks to be,
Safe bases are like a matching exactly.
yeah.
Very nice.
We have this, and this is somehow problem, and then, like as I said, we have a proof of this theorem, but we never published, and then Efremenko say, hey, guy, look at me. Oh my God, we have this for almost a year, and I didn't know how to use it. It wasn't good like Christmas present. Yeah, but when we have this, then Srijato said something. Oh, it looks like whole condition and blah blah blah. And I look at the proof of the whole theorem. Yeah, exactly. Like that's what we need. Okay, so we say a set of block is an obstruction. If, like, when we take is an abstraction of U, this U, if like when we project outside T, so we project on this vector space on the blocks outside T, then we get a spread space. Now this projection is spread. Right, so
Structure of view. So this is another definition.
yeah,
You're not going to prove the theorem, I guess.
this one.
I'm happy if you don't.
No, I'm not. I prove it as I said it was Gaussian animation with dots.
So
So this is another.
it's another thing.
So we have some T blocks, right?
Oh, I
We
see.
can we just throw them away, and what is rest? It's a spread space. It means it has the same basis. What's another nice about abstraction? That if you take a minimal abstraction, inclusion values, that's unique for a affine space. So a minimal abstraction of U is unique. We also know that, also proved by Efremenko and Bishop. I'm not proof. These things I'm not gonna prove, but
The section of two obstructions is an obstruction.
yeah. But it's all of these are can be proved by like standard linear algebra. And so is unique. Let's say the minimal, and the abstraction is small. And the size of P is at most dimension of U. So, like a small codimension affine space cannot have a large abstraction.
Dimension or codimension?
Like it's a codimension of the affine space. U is the space of constraint. So take U to be the rows of the matrix. Right. So dimension of U is codimension of these sense affine space. And so from this, another definition is that say call it Efremenko call it closure of the affine space A is the minimal obstruction of row space of the matrix number. A is a defined by matrix. So we have this disclosure, and now what can be proved, and this thing is I think new. It's not in the Efremenko thing. If we have this notion, we can like change the matrix M to basically by linear operation into that M has a following form, and it defines the same affine space. So M can have the following form. So let's have these blocks. These blocks are to be the closure of the affine space. Right. We have some matrix here and prime. Here are zeros, and here we have same matrix. And now, and you can have this for any affine space. Now this is the general case, right? I say if M is safe, then the whole cube has a pre-image in the. Now, if you have this matrix, right?
So maybe you fix the values of inner product on the closure of A space,
Then
but elsewhere you are
exactly. So if you have a cube which fixes the the bits corresponding to the closure, right? And these bits are such that they have pre-image in this subsystem, right? Then this whole cube has a pre-image in the affine space.
Sorry,
Right? So let's have this. So again, A is mx equals c, right? Maybe and mx equals like c1 c2, right? So now you have cube c of like on n bits. Right? What are the entries of C? Right? You fix some bits to alpha, and then any combination appearing on the reference, right? This are small. Like what are the entries of the cube? Something like this. Take alpha, right? And take if there exists beta, which is a pre-image of alpha, such that n primes beta equals c1, right? Then like this cube is in the affine space if you apply the inner product, right? On the affine. Each element of the cube has at least one pre-image in the affine space, right? Why? Yeah, because like affine space is a subset of right? So if you apply right? Why is it? You know that like alpha has a pre-image in this subsystem, right? Here are zero. So if you extend alpha to anything, these constraints still holds because they don't depend on these values, right? And these are safe constraints on these set of blocks. So any vector has a privilege. So now, so we have this notion of closure. I'm almost there to define what this full ability is. It depends on also on the hard distribution. So, are you okay now with what is the closure, and can I erase it?
It's don't know why it's called closure.
It's a name of Efremenko. I don't know. Like we call it obstruction and minimal obstruction, but Efremenko call it closure. So somehow we want to keep the same notions and same names. So, yeah, maybe the reason is it's because of some like field I don't know about it. So we have this notion of closure, and this stifled gadget. And so what, as I said, like we need to define hard distribution of this unlifted form, right? So this distribution now fix fix the stone placement, like all assignments sampled by this distribution, like the stones are placed on the same vertices. So we have some mapping bijection, bijection F. Our distribution. So we have fixed bijection from stones to vertices of the pyramid graph, right? So we put stone I on the
Sure.
so stone I.
There's one stone per vertex, and that never changes.
Yeah, that this is fixed. This is not random.
Right. So every variable p v j will be there will be for each v there will be one j. Which
And we create somehow blue path from the root to layer n minus one. So there is exactly one point where and we set these variables accordingly, right? So
only one unsatisfied.
yeah, exactly. Like
so
we are in obfuscation world, right? So one of two clauses is falsified, right? Because we have is it somewhere here or I use it. But I will write it. So we create like a random walk in each node we go with a half probability left, the half probability right. So it's a
so you choose a random node on the n minus one layer.
no. It's true that like we somehow end with high probability in middle. So like the nodes has a binomial, the n has a binomial distribution, right? But we sample some group R. We call it P, right? The rest of the vertices are red. So. And so we have this Google path P. We have end of this Google path called P, and the children of P is the U and W. Right. This is a layer n minus. So with the notation I erased, right? So the only unsatisfied clause is the induction clause on vertex V, right? With the stones which are put into V, U, and W. So it's like an inverse of the function.
But we can just call them U, V, and no?
Huh?
So you can just call them V, U, and W, right? Because might as well. You know? That's what
Yeah, something. In some arguments, we want to prove, like, I will probably not to get there, but it was for arguments that because in some arguments we change the stone placement to full the fine space, but so the only unsatisfied clause is this or this, right? And this is the hard distribution, or mu, and then of course the elliptic one is. And now, finally, what does it mean to be alpha full level? What's the alpha full level? So we have a set of blocks, and we say this set of blocks, this alpha is some alpha that is supported by me. So we say this set of blocks is alpha full level. If T does not contain any variable mentioning U, V, and W. So T is set of blocks, but also like the blocks corresponds to variables. I will explain more, but the blocks corresponds to the variables of the unlimited formula, right? Alpha is some sample of the mu, so it induces this coloring. V, U, and W are the ends and the beginning of the blue path. What's variables mentioning
now for every
so these variables are either Pxi or Zxj, where X is one of these. So what it says, these blocks does not know anything about the stones what are on these three things. So like what we show later is basically if we restrict alpha to T, then we can place any stones on these variables. And somehow make it to
But not any, some stones might have already been placed somewhere else.
like sure, but like one thing, the constraints, as I said, does not follow that you put exactly one stone to like there has to be at least one stone on each thing, but you can distribute one stone to assign one stone to.
So your
But,
distribution does
Like what is it meaning? Basically, T will be closure of the affine space, right?
Yes.
Closure is something the affine space fix, and you can change the other things as
But
you
not
want.
T, right? So T you cannot change.
But if T, right, does not know
Any such variable.
any such variable, right? Then you can somehow put different stones here, right? And change the only unsatisfied clause, right? And still this clause will have there will be in your affine space an assignment that falsify only the other one. That's somehow like what's the thing?
Oh.
So now when you have this definition, there are two inequalities, right? One is that if you have full level R, sorry, this is only part of the definition, sorry. One I only said, we say that affine space is alpha full level.
If its closure is alpha.
If E is alpha full level. And there exists beta in A that alpha is beta is this one, right? Like alpha is and if so now and so just like introduction to how to prove this two inequality. So this part requires the bottom regularity. So this inequality that the alpha full level affine space has a large codimension. And this part, as I said, for this part, like the strategy is if the probability that this random affine space is alpha full level is small, then we can construct a decision tree for or parity decision tree for like randomized parity decision tree for the problem that you are looking for falsified clause of lifted stone formula, right?
Succeeds with.
And by the simulation theorem is hard also for for standard decision tree. So
You mean
this inequality is proved by some lower bound and lifting in for a decision tree. So From
So, and
so
what you're gonna
from
do is you take your program, you throw away every node where this is not alpha foolable. That's it, and you see what you have left.
it's like the proof is like make these steps in your affine deck P, right? Extract a decision tree what you get, right? And so maybe I don't know, take only short sketch how to prove this inequality. So you have your affine deck P. Make T steps and consider only query nodes and extract a decision tree. So we have or you have parity decision tree T. Somehow for search problem on this formula of this problem.
Okay, so what do you output actually? What's your output?
Like basically you simulated these queries, you end in some affine space, right? And then you query you query all variables that are mentioned in the closure. Let me check. Now it's not hard, but a little bit technical. But you look at the closure, right? And how is it? The thing is, first, it's a randomized parity decision tree, and the distribution is a mu on mu, right? Mu fix the stone placement, so you can only query the somehow colors of the things, right? Of the stones. So for any nodes in this that is mentioned in the affines in the closure, you mentioned the color of the stones which are on them, and somehow you can show that if the affine space is not alpha foolable, then you can discover this falsifying thing. Basically, so suppose vertex X, right, of the pyramid graph is mentioned in this sense in the closure, right? You look on vertex X, and you vary the colors basically of the surrounding of X, right? So you vary all these the colors of this surrounding of X, right? Because of the closure of the affine space has size at most T, then you vary at most like T log n variables, right? And if the affine space is not alpha foolable, then somewhere in this X is somehow part of this thing, right? So you discover this thing. And in that case, otherwise you will put error symbol if you don't discover this.
Or a half or something.
Yeah, or something, whatever. Like a half is not the correct answer because it's a search problem, but whatever, like you don't care. Nothing, right? So
now
if
your
the probability that the affine space
is not foolable
is small, is not alpha foolable, is large, right? Then you have this, you have like
you have a low complexity. Which
which
also
is
the, yeah,
correct, is the same probability,
With the
so 3/5.
its complexity is not much bigger than.
And like the height of the tree is at most like T organ.
Mhm.
By lifting theorem, this heavy machinery lifting theorem for communication,
Hmm.
right? We derive no, it's not.
Decision tree for,
Yeah, the thing is,
so the only,
we have,
yeah.
we prove a lower bound that decision tree P for like unlifted problem.
Right. It's an upper one, no? Is that most steep?
Uh, this is upper bound, yeah. But we have this such that the probability of
Break is still roughly big.
is still
Roughly three.
1 minus epsilon, then such P prime, then
No, it's not 3/5, it's like 2/5. But it doesn't matter because you have a
Yeah.
lower bound.
yeah, we have a
But
lower.
it's not a lower bound, it's an upper bound. And then you invoke the lower bound that came from the previous paper, right? Is that right?
Like how is phrased, maybe you say the same thing, but how is it phrased in the paper, right? Then if you have a decision tree T prime for this problem, which has a high probability of correctness, then a height of this decision tree has to be at least omega n to 1. Right, and by this lifting, we have a lower bound for T.
Yes. Oh, I see. But this comes from the previous, is that right? This lower bound?
No, it's
Oh,
this lower bound is proved in our paper. I don't know if there is like
Oh, you prove randomness, so.
it's a randomized lower bound.
okay.
It's a randomized lower bound, and it basically says that right, because like here are two strategies. There is a strategy in this for as I said for this distribution. Then you check like square root of n middle vertices here, right? And you discover this thing. Right? But we prove like the smaller unmatching lower bound, right? So you cannot use this strategy. And the other strategy, which is like even worse, is to follow this path, right? This is the other of the like natural strategy. If you have this limited communication, we somehow prove that if you follow this path, you somehow have to make like jumps, right? That you try to find like this blue vertex and the other vertex, you try to find like in long way, and it can be fairly like arbitrary, and you cannot. So this is all. Okay, so this is like this should work.
Right.
Do other proofs of lower bounds for regular resolution also prove probabilistic?
Efremenko in like that they reduce the lower bound for like regular ResLin to probabilistic lower bound. The lower bounds for what I know for like ordinary resolution, they don't really work. Okay, so somehow the only things what remain is this thing that when you have alpha full level that
You should not put up.
and you should have a large range. And okay, so and also this is the only case where we need some property of the this inequality. The only case we need some property of the obfuscation map. Any other else, everywhere else, it's like it holds for any obfuscation maps, and it's maybe like a burden that we need to prove it also for that it is there, but yeah, it's strange that as I said that we need this stone placement thing and the obfuscation both. Then the separation for regular and ordinary resolution is done like only with one technique, but somehow we cannot. I think like it should be proven that using only one technique, but somehow we cannot do it. Okay, so what's the theorem? So there exists this obfuscation map such that for
Here, obfuscation map can change. Based on them, it's fixed before it's part of the problem set.
yeah. If you have any assignment, then T and when we know in the defined egg, follow this assignment B for T steps, then if the affine space under node P is a alpha full level, whereas alpha is a D-dice primation. So if we apply linear product on beta, you get alpha. Then codimension of AP is bigger than n over 300, and so this part is just like this n over 100 is just a technical thing. In our case, t will be always smaller, right? Because we can prove only this part for t to be n to 1/3, small n to 1/3. Capital N is a number of nodes of the pyramid graph. Small n is number of layers. So basically, this inequality, I understand that it's bigger than t. It holds up to like some bound which t never achieved in our proofs. Okay. So first, let's talk about the one lemma. And as I said, it's a it's about the changing of the only falsified clause. So this lemma even holds for any obfuscation. And it says the following. We have some alpha that is sampled by the R distribution mu. We have some set of blocks that is alpha full level. And we have a UT, which are the set of stones mentioned by T. So alpha fullability is about the vertices of the pyramid graph. This QT is about stones. So what does it mean? So UT is set of stones. And how is it defined? So J is in QT if any RJ is the color of J, or PJ, it's if J is on the vertex E or not, or PLJK, or the JL is in T. So we say that a stone J is mentioned by T if at least one of these variables. So either like the color of and the placement is mentioned by T of the stone J, or if the vertex where the stone J is placed by mu is mentioned in T. So if any of these variables is in T, we put the stone J into T. So this alpha fullability says something about vertices, and we can somehow change the stones on the vertices. If a stone is not in QT, we can place it somehow. We are free where to place it, the color. We have no information about the stone J if it is not in QT. And so we have this set, and our assumption is that the size of QT is at most half. Then for any triple IJK of stone that are not in QT, there exists assignment gamma extending alpha T such that the only qualified clause by gamma are the following induction clause. IJK or rho IJK or IJK or not rho IJK. So
IJK are stones.
IJK are stones. So like the proof is quite straightforward, but technical. But like,
For all stones not mentioned in.
yeah, like, if you decode it, what is said? We have some assignment
Mhm.
that is the alpha full level, and we have some set of variables that is alpha full level.
Meaning it does not mention the
So-
important nodes for.
Yeah, so this T does not mention this.
Yeah, okay.
And also, this T does not mention the triple IJK.
Right.
So it
So
means basically,
okay, some triple could be that one, could be some other one
Yeah.
that he doesn't mention, yes.
it says that because T does not mention this and the IJK, we can put the stones IJK here,
Oh,
set the colors,
yes.
right? That like the original falsified assignment is this, right?
Hmm.
But if T is alpha full level and does not mention IJK, we can replace this thing by IJK, and we somehow get new induction clauses that are falsified.
Yeah.
Uh,
So, replace, yes, replace.
right, the thing is,
Yes.
gamma is not anymore in the support of mu.
Mhm.
We don't like because like we put difference. The thing is this is like deterministic thing, so this P should work for any assignment, not only for the support of mu. So this is like legal operation.
Oh. Wait, but
Uh,
how do you know that this particular gamma, right, would end up in the same node? It might not.
it's the thing, right? I didn't mention the same thing, but this T would be again the closure of A, and this gamma would extend the assignment on the closure,
Mhm.
right? So what is not in the closure, you are free to change, and you still.
No, okay, so there's like this basic, right? Because you start at the root. Let's look at what happens when you start at the root with some pre-image of alpha. Now we know that we're gonna end up in this node P, right? But now we've changed alpha, hence we've changed the pre-image for this other node. Why would we end up in the same?
Maybe we would end indifferent.
Right.
But the thing is, you are in deck, and you like this is the thing where the branching program is different, right? Because you are in deck, which somehow arises from the proof,
Right.
and like you have to be correct somehow in all elements in your affine space which are labeled on the node. Like there isn't like this very forgetting things is a little bit artificial for the things like
So,
this.
what I expect that you're gonna say, let me, tell me if that's what you're gonna say, is that if I now start at this node P, even with gamma, I have to end up in
Yeah,
the
the
correct.
gamma, now the gamma appears somehow because of forgetting maybe.
Yes.
But this gamma, because it appears again, it still ends in some something. Because
Yeah.
you introduce it as well, you need to work with it.
That's
Yeah.
actually also true for branching programs. Where instead of subspaces, you have subrectangles of the Cauchy-Richardson game.
Yeah.
It
Like
doesn't have a structure.
the objects on the nodes in branching program are more difficult.
Yep, yep.
Yeah, but the proof of this lemma is
So, okay,
I'm
so you're
not
saying,
saying how to use it so far, but
right, so what you're saying is that, so I just end up in this node by following some beta.
so far this lemma says nothing about that, right? It says only that if you have some assignment alpha,
Sure,
right, and some full level
I agree with
subset, then you can change it.
I agree with the limit, yes, of course.
Okay, so now how to use it, right?
Why does it have size less than half? Or is that just?
That's, I don't remember, but, yeah, that's, yeah, I don't know, right? Okay, so now, let's look at the proof of the theorem. Well, let's look on this equation. We have P, right? We make T steps on some random input beta. We end in node P. Now look on all path that goes from P to sinks. So let denote this subtest. Also suppose that codimension of AP is at most n over 100. Right? You have the space AP. Okay, now so maybe so need one claim, and yeah, I said this one multiple right because this lemma is used for prove this claim. But let's claim about this picture. So let's take any variable y of our listed polynomial, and the claim is there exists a sink in S. So these sinks in S are labeled by the clause of this. These are the problem. So so there exists a sink. I will put in a clause D such that y is present in the clause. So meaning like literal containing y, so it's a y, or not y is in P. So I will comment more the proof of this, but for this proof, you will need this lemma and the obfuscation lemma. That somehow the obfuscation method will help you to okay. And if we have this, so let's finish the proof of the theorem, and then I'll comment more on them.
Sure. I mean, that's just because every variable is important, right?
Yeah.
I mean, choose any variable v, right? By setting every other variable except for this one, I can make every clause that doesn't contain this variable satisfied. That's the claim, right? If I take any variable v in this particular program, right? Fix a variable.
Yeah, but the thing is, you are already here, right? This S set is not set of all things. It's a set of things reachable from P, so, this is, you need to show that this is also true when you are already here.
Oh, so wait, so S is not the set of all things.
No, it's things that are reachable from P.
And what's the assumption on is only the only assumption is that the codimension is smaller than n by 100?
Yes, yes, yes.
No fullability.
Huh?
No fullability.
Yeah. The assumption is that AP is also on. That's it.
Okay, so the claim is if AP is alpha fullable and has codimension less than n by 100, then among the sinks under P,
Every variable is.
every variable.
So every variable is still important here. Yes.
Wow.
Okay, so now let's take like affine space U.
You're gonna prove this, no? That's not
no.
obvious to me.
You want to prove claim or theorem first?
Oh,
It's up to you. Like I can prove.
I think I would claim.
Claim?
I'd like to see the claim.
Okay.
This is not.
Then let's talk about the claim.
Yeah.
So now there is the part about when I was talking about what's a lifted formula. I said that like 2 hours ago. We are there.
Yes. Every variable, what was it? Something.
So let's prove this claim. Let's take Z. So we have some variable y.
Right,
And
the theorem will say that either you've already found, well, if you haven't found it, right, if you haven't found the right set of nodes,
then you need to remember basically everything.
then you need to remember basically everything. Where does the T come from, the little T?
P is the length of this part.
I need to remember at least T or everything.
Yeah, like T is like the number of queries you can make, right? Because so it says that because this has a codimension at least T, right? Then it means on this path you made T queries and you cannot forget them. So to prove the claim, we have this variable y, and Z is a variable of the unlifted formula, and y is in the block of Z. Right, so y was introduced while lifting. Now, T would be the closure of AP. And now, the property of rho. So, the size of P is at most n over 100. Right, by this assumption. Now look at this one variable that is in T can mention at most 2 stones, right? This variable basically PFJK mention stone J and K, right? So it means that the size of QE is at most twice the size of P. So it's n over 400. Now, the property of overall is such that for Z,